let's take a moment to do a brief overview of all of the techniques. So you might be given the problem of line integral of a scalar field or a scalar function. So the usual one with a ds, or maybe with respect to x or y, or perhaps with respect to z. And you can always take this problem and parameterize the curve c and set up an integral, a single integral that uses t as your parameter. If you have the line integral of a vector field, you can always parameterize the curve and set up a thing like this. Also, maybe I should note here that if you had this first one with the ds, you could rethink of it as this problem here. Why do that? Well, instead of parameterizing the curve c, you might have another option. If the vector field you're integrating is conservative, you could apply the fundamental theorem of line integrals and find a potential function, lowercase f, and do this kind of thing instead. And as a special case of that, if the curve happens to be closed, so on top of capital F being a conservative vector field, then you just know that the answer you're going to get in the end is 0 because you're just taking a number and subtracting itself. But there are a couple other things we can do as well. So instead, you could take this problem that's in this green box. By the way, everything in a green box here, it might be the original problem you're given, the original exercise. If you have f is a two-dimensional vector field, f equals pq, you could convert it into something that looks like this. What's really going on is you first interpret the integral like this and then apply Green's theorem. Okay, of course you can use Green's theorem backwards. You can take this and take an integral that's integral over the curve c of a function p with respect to x plus a function q with respect to y, and you can always reinterpret back this way. And when you do have that double integral, say that you get by applying Green's theorem over this closed curve, then you can take that double integral, and then as far as actual implementation, turning this into an iterated integral, you might turn this into dx dy, or a dy dx, or an r dr d theta. On the other hand, this line integral of a vector field, it might not be a two-dimensional vector field like this. You might instead have a three-dimensional vector field, and C is a closed curve. Then you can apply Stoke's theorem, and then you're down here. Or this problem might be the original one you're given in the first place. But if you take the line integral from earlier, if f is a three-dimensional vector field, you might set up a surface integral that looks like this due to Stoke's theorem. And you could take that integral, or if you just presented this as your original problem, you can convert this into just a standard surface integral, or again, what's in green here just might be the surface integral problem you're given, and you could parameterize S, or you could ignore this implicit S thing. That's just another way that surfaces can be described, but let's not go there for now. You could also have S is described as a graph of a function, and so you have this integral, double integral over a certain parameter domain, and then this turns into, in the end, an integral du dv, or an integral that's dv du, or an integral that ends r dr d theta, or perhaps some kind of substitution is perhaps nicer instead. Okay, so that's one thing you could do with the integral of the curl of a vector field over an orientable surface, or you could apply Stoke's theorem again, right? You could apply Stoke's theorem again and have a line integral, or you could apply Stoke's theorem another time and have, a second surface. So you have a surface S, and then you have a new surface S prime that both have the same boundary, and you have this problem like this, and you can take this integral here, and then you have one of these, and then you can figure out how to implement. Or, of course, you could take this line integral that appears right here and go back to the things we saw earlier and implement that way. Finally, you could have over here the problem of integrating the flux of a vector field across a surface, and you could just compute that directly and land yourself over here and then do one of these things. Or if you have S is a closed surface, you could apply the divergence theorem, and you have the triple integral over solid region E of the divergence of F. There should be no dot in here, apologies about that. Or of course you could use the divergence theorem backwards, but then when you have this triple integral here, you can turn this into a dx dy dz, or a dx dz dy, or so on and so forth, or into an r dz dr d theta, or into spherical coordinates, or perhaps something with another substitution and using a Jacobian might help. So it's a lot of different options here, and the point really, zooming out just for a second, is that everything in a green box could be a problem that you're handed, or you might do a lot of converting back and forth, and you've got to sort of practice what's going to happen. Is this going to be more helpful? Is that going to be more helpful?